Hello and welcome everyone. It is November 13th, 2024. We're live and kicking off the fourth Applied Active Inference Symposium. It will be a great program, and we will begin with Carl Friston and Lance DaCosta discussing scale-free active inference. We discussed in livestream 58.1 with Lance last week, and in 58.0 with Arun 2 weeks ago, a bit about this work. And today, Carl, thank you so much for joining and presenting on it. So, looking forward to it. And throughout, in the live chat, please feel free to write any comments. Thanks again, everyone, for joining and looking forward to this.
Well, thank you, Daniel. It's a great pleasure to kick off the symposium this year. I'm going to rehearse a presentation I made at the Active Inference workshop a few months ago, but this time I hope in a slightly more relaxed and unpackable way. So I'm fondly hoping for lots of questions and embellishments from the audience and from Lance. This is a bit of a colloquial presentation. It's just going to focus on something specifically that we've been working on for the past few months, which is effectively addressing the question, how can one scale active inference for high-dimensional real-world problems? And the solution that we've been pursuing is to adopt a scale-free approach. This work has been written up and put on archives. However, it's also been submitted for publication, peer-reviewed publication, to a special collection in memory of Hermann Haken. And we've equipped the peer-reviewed version with a little foreword. So I just wanted to frame or preempt the scientific part of this presentation just by motivating why the work of Hermann Haken is foundational and underwrites many of the ideas and procedures that underlie this scale-free approach to active inference. So Hermann Haken was famous for synergetics, a physics-led approach to self-organization, and in particular the importance of understanding the coupling between different scales of dynamics in self-organization. And if you go to the Wikipedia entry, you will read about macroscopic and microscopic variables and how they are coupled to each other in the fashion of circular causality. So there's both bottom-up and top-down causation, where the top-down causation is sometimes read in terms of the slaving principle. I'm going to present this approach to harnessing this notion of a scale-free universe in terms of installing that scale-free aspect in the generative models that we bring to the table to solve decision-making, to simulate or emulate active inference under discrete state space models. So let me start at the beginning. The nature of things and the free energy principle. And this is just to rehearse the fundamentals of the free energy principle. It all rests upon the notion of a Markov blanket, where we can separate internal and external states by boundary states or states that constitute the Markov blanket, namely the sensory states and the active states. And for those people not familiar with this particular partition of states of any random dynamical system, it's just specifying systemically a system, say a brain, in terms of its inputs and outputs, and just formalizing the conditional dependencies that define what is an input to a brain or an agent and what is its output in terms of the sensory and active states, that thereby render the system of interest, in this instance a brain, open to the environment, the eco niche, the heat bath if you're a physicist or a chemist, in virtue of the fact that the inside can influence the outside via the active states, the outputs, and the outside can influence inside via the sensory states or the inputs. And with this setup, we can elaborate a kind of physics, namely Bayesian mechanics, that is almost, well, formally related and inherits exactly the same mathematical and functional form as all the other mechanics that we find in physics, including quantum mechanics, statistical mechanics, and classical mechanics. The only thing that separates the Bayesian mechanics is the fact that we have in mind explicitly this partition between internal states and external states, and the blanket states that intervene and couple the internal to the external. And that Bayesian mechanics is effectively summarized here in terms of variational and expected free energy, where we can read the expected free energy as effectively prior beliefs about the kind of outputs or actions that, in this instance, a brain could exert on the external states, and the variational free energy keeping implicitly the internal states a good model, so it's tracking in a probabilistic sense the dynamics on the outside, and we can combine this to create a generalized free energy that now teleologically or perhaps even anthropomorphically, we can now read the gradient flows that subtend this Bayesian mechanics in terms of action and perception just by identifying the internal and active states of any agent as autonomous states and noting that they effectively flow on the same free energy functionals. So that's the basic setup. But what I want to do before applying the free energy principle in the service of things like active inference is just back up and reflect upon the fundamental role of the Markov blanket and how that leads to a scale invariant picture or view of dynamics and self-organization. So what I'm going to assume is that ultimately we will assume that Bayesian mechanics means that the dynamics of anything that is defined in terms of its boundary or Markov blanket can be described in terms of active inference. But before that, we have to think about the nature of things. And in particular, if one goes back to the particular physics paper, the nature of the states that constitute things or particles. And there's a bit of a subtlety here, because before you can start talking about states, you really have to define what is a state. Is it the state of something? Is it the state of a particle? And that presents an issue because you're defining a particle in terms of this particular partition into internal, external, and boundary or blanket states. So there's a slight not tautology, but there's a slight problem in resolving how you define states of things or particles and particles that possess states. And the resolution of that is to adopt a recursive definition so that the particles constitute a set of microscopic blanket and internal states, while the states are a set of macroscopic eigenfunctions, eigenmodes, or just simply mixtures of the blanket states. So I'm here deliberately using the notion of macroscopic and microscopic states just in as a nod to synergetics, and in particular kind of synergetics that Hermann Haken developed and subsequently championed. So this is cartooned or illustrated on the right-hand side here. So we sort of take some states and then apply a particular partition on the basis of which states are coupled to which other states and the conditional independencies that ensue. And then, having done that, we can then take mixtures, eigenmixtures of the boundary states that then generate new states. And then we can effectively, by taking those mixtures, we effectively reduce the dimensionality so that the higher scale coarse grains the lower scale, and then we reduce it, and then we just rinse, wash, and repeat. And we do that, and every time we sort of pass through this cycle of RG operators, reduction and coarse graining operators, we move to one scale above successively. And this is the scale invariant aspect of that I want to leverage in the remainder of this presentation. I use the word RG deliberately because one way of looking at this or articulating this is to use the apparatus of the renormalization group. So this is where renormalization gets into the game, that you're recursively applying these operators, coarse graining things, in a way that conserves their dynamics, and that's an easy criteria to meet for us, because we know that anything that has a particular partition can be described in terms of a gradient flow on a variation or generalized free energy. So we have everything that we require in order to apply the apparatus of the renormalization group. So what that basically does for us, once we recognize that particles are composed of states, where the states are eigenmixtures of particles in this scale invariant fashion, gives us a view of any universe that comprises things of things of things, as inherently resolving a chicken and egg problem through scale invariance by application of the renormalization group. So here's just another illustration of how that actually works in practice when you write down the equations. I'm not going to bother going through the equations. This is just used iconically, just to make the observation that as you move up scales, so for example, in an evolutionary context, this would be the sort of the dynamics of phenotypes, and then we move up to the an evolutionary scale by effectively coarse graining in a way that Hermann Haken would exactly prescribe in terms of taking those slow macroscopic variables that decay very, very slowly, which are technically the eigenmixtures equipped with very small eigenvalues whose real part approaches zero from below, effectively saying that these patterns decay very, very, very slowly, and they have a kind of persistence that lends higher and higher scales a temporal dilation, so things change more and more slowly as you increasingly coarse grain things. And that this falls out of the maths when you simply apply a particular partition and put that partition in as the coarse graining operator in this scale-free formalism. So, in short, Bayesian mechanics entail a generative model of external dynamics, but we've just seen that just by defining things in terms of particles that have states and defining states in terms of the eigenfunctions of particles, that external dynamics are inevitably scale invariant. It can be no other way. And therefore the generative model must be scale invariant, or when expressed as a graphical model, scale free. And I just slipped that in as a nod to the fact that people often talk about scale freeness. Generally speaking, when people apply the notion of scale invariance to anything, if that thing is a graph, then you can call it scale free. So a scale free thing is a graph that has this scale invariance. Crucially, in both time and in space, because we are dealing with dynamical systems and we're doing this dimension reduction or coarse graining using these eigenfunctions that necessarily pick out these slow macroscopic, sometimes called stable modes. They're stable because they don't decay or dissipate almost infinitely quickly. So they're stable in the sense that they decay very, very slowly. So how can we harness that observation, that truism, at least truism under the world as described by Haken, in the construction of plausible generative models, and in particular generalized Markov decision or partially observed Markov decision processes? Well, what we can do is we can just look at the different kinds of depth and ask at what point would we be able to leverage this renormalizing aspect of the cause-effect architecture of any given world that we're trying to navigate and predict. So here's the normal depiction of a generalized Markov decision process. And by generalized, what I mean is that there's an explicit representation of not just the states of things that are generating outputs or things that can be measured or observed on the sensory sector of a Markov blanket, but also their dynamics in terms of the paths that specify the transitions between states, as we know, normally encoded in terms of a transition tensor B here. So just by putting in the paths as explicit random variables that accompany for each given factor the hidden states, we have a generalized kind of Markov decision process encoded in the usual way, in this instance, in terms of tensors that themselves can be parameterized as Dirichlet distributions. So that parameterization equips these kinds of models with a parametric depth, in the sense that if something is deep parametrically, that means that the parameters of various probability distributions are themselves random variables that have their own probability distributions. So, for example, the likelihood mapping that maps from sensory states to outcomes here, usually encoded by an A tensor here, mapping from latent states to observations, is itself encoded in terms of Dirichlet parameters, lending this kind of model a parametric depth. And one can ask what the implications of that are. Well, the implications are another kind of depth in terms of you now have to optimize or apply Bayesian mechanics to the latent states, the hidden states, and that would be inference. And then you also have to consider at a slightly slower time scale the optimization of the Dirichlet parameters, and that would correspond to learning, and so on. If I wanted to go to the structural learning of the model in and of itself. We also have implicitly a temporal depth, in the sense that we're going to be rolling out into the future and that there are dynamics here. And this temporal depth is generalized in virtue of having these explicit path variables that we're going to exploit later on. We can also have hierarchical depth, in the sense that we can compose many Markov decision processes in the sense that the outputs of one process now constitute the inputs or the empirical priors, the top-down constraints, the inductive biases on the dynamics and states of the level below. And the dynamics are the kind of outputs of the upper level that provide empirical priors on the paths, and the initial conditions are supplied or mediated by a mapping between higher levels, slower states, and the initial conditions or initial states of the lower level by this D tensor here, that you can lump together in terms of a sort of high. You can lump together the D and the E tensors. They play the role effectively of the A tensors in sort of mapping from one level to the next level. There's also a factorial depth, which many people will be familiar with, in terms of for any one of these lumped states here. There may be many, many different factors that have a certain independent structure such that you have interactions between factors in determining outcomes. You can look at this in terms of a generative model, when equipped with factorial depth, effectively entangles latent states to generate outputs or outcomes, which themselves can be prior constraints on the states and dynamics of the level below, such that the inversion of these models effectively disentangles the data or the content that is being observed to explain it or in terms of a disentangled representation, which is the latent state and dynamics of the generative model. So what we have here then is a generalized discrete state space model with paths of as random variables. Just to return to this fundamental aspect that as one ascends scales in real life, in terms of the external states, things slow down in virtue of the synergetic mapping from fast microscopic states to slow macroscopic states. The same thing can now be implemented in these Markov decision processes that have a hierarchical depth. And the way that is done is effectively to discretize or quantize time, such that there are more updates at any given level than the level above. So for every update at this level, there are say 3 updates or 2 updates at the level below. And that affords a temporal scaling in accord with the scale invariance implied by the synergetic view of self-organization. And I've tried to cartoon that here in terms of, if you imagine lots of these little Markov decision processes populating this circumference here, and that as we go deeper and deeper and deeper into a model with hierarchical depth, as we consider updates in universal or clock time, there are more updates at the peripheral level exposed, say, to the external states of an entire brain, relative to the updates that as you get deeper and deeper and deeper into the model. So that's where the temporal depth becomes, if you like, intimately tied to the hierarchical depth. The higher the hierarchy, the slower the updates, which is why we generally parameterize the initial conditions or generate the initial conditions and the initial path from the states above, and that path can pursue a trajectory over multiple time steps until a certain horizon, in which case it then sends messages back to the level above, likelihood messages, that then cause belief updating in the subsequent step at the level above, and then generating priors about the subsequent path, the next path at the level below, and then so on recursively to the depth of the model. So that's the time bit. What about the spatial bit? What about the sort of spatial coarse graining, the lumping together of various states? And of course, this depends upon the particular partition. So in the general physics formulation, you'd be looking at Markov blankets and Markov blankets. In practical applications, one can take a shortcut. And that shortcut effectively rests upon the simplifying assumption that for most systems that are composed of coupled dynamical systems, the interactions are usually local. So if we just think about some system that can be described in terms of local interactions. So, for example, in a Euclidean world that comprises some massive objects that bounce around. And if we ignore gravity for the moment, then they're only going to influence each other or depend upon each other when they're touching, when they're proximate. Effectively, what that means is that the particular partition that defines all the Markov blankets in this particular state space is composed of lots of local little tiles. So what we can do is we can use a device very prevalent, or indeed ubiquitous, in applications of the renormalization group, which is called a block or a spin operator that just groups together local tiles or quadrants of a, say, two-dimensional arrangement of of states. So I've illustrated that here just by in terms of how we do the spatial coarse graining in these what we will refer to as a renormalizing generative model with spin block transformations in terms of this little this hidden state or hidden factor with its states and paths here is responsible for generating predictions about the dynamics of these two factors at the lower level, and in so doing, what we are effectively doing is successively grouping together sets of sets of sets of sets, so that any set or group at one level is accountable for or trying to generate the dynamics of a small local group at the lower level. This is quite fundamental. This kind of architecture is quite fundamental, because what that means is anything at the lower level only has one parent. And if it only has one parent, and if you remember, the Markov blanket is constituted by the parents and the children, the parents of the children, because there are no co-parents, there are no parents of the children. And what this means practically is that we can now ignore dependencies between, or effectively resolve or dissolve any dependencies between the factors at any given level, because each factor is only responsible for its children, and it doesn't share any children in virtue of this particular spin block transformation. So this leads to a very efficient kind of generative model, or certainly an efficient kind of inversion of the generative model, where we've got all these converging streams, but the streams don't have to talk to each other until at the point that they come together through these blocking or spin block transformations. So at some point, all the tiles or the groups at the lowest level will actually come together at the top or very deep in the model, at which point we're now encoding quite long trajectories, technically 2 to the power of the depth minus 1 in terms of updates. But at the lower level, there are no interactions between the different blocks as we ascend them. And this is just to remind you, we can treat these D and E, the initial states and the initial paths, effectively as likelihoods that couple one scale or level to the scale below. So how if that's the kind of model that we aspire to, because we think that's appropriate for any world that shows this scale invariant aspect in space and in time, or in state space and in time, how are we going to build one of these things? And this is the sort of second, if you like, thing that we have been working on, because it's going to be very difficult to specify by hand these scale-free or renormalizing generative models. We really want the model to learn itself. So basically, how does one build a renormalizing generative model? And what we're going to do, we're going to use very fast structure learning. And this particular kind of structure learning is necessarily recursive, and in the sense that we're going to build these models through the recursive application of these RG operators, or renormalizing operators. So what's fast structure learning? So fast structure learning basically equips the model with unique states and transitions as they are encountered. So to put that simply, what we're going to do is grow a model from scratch, from nothing. And how we're going to do that? Well, we're effectively going to take one observation and say, okay, that was generated by some latent state. And then we're going to take the next observation and say, okay, I haven't seen that particular observation before, so I'm going to induce a second latent state. And furthermore, I've seen these two observations in sequence, therefore I'm going to encode that with a transition from the first to the second state. And then I just repeat. I take the third one, and if I haven't seen that before, I induce a third latent state and a second transition, accumulating all the unseen or unique instances of observations in a likelihood mapping that just grows and grows and grows until we have seen something before. So we don't induce a new state or implicitly column of the likelihood matrix if we've seen the previous state. That's just an instance of something that has been seen before. It may well now come along with a different path, so the next state may not be the same as the subsequent state following the previously seen instance of this state, and therefore I'm going to induce a new path and slowly grow my B tensors and my probability transition matrices until I can basically encode all the dynamical structure of effectively the training sequence of observations summarized in a maximally efficient way. And I mean maximally efficient in a technical sense, in the sense that the implicit mapping that we are growing from scratch has the highest mutual information between the latent states and the observations that are at hand. The way that you can think of that in terms of free energies, that the expected free energy is just the mutual information in the absence of any expected cost. So the expected free energy is just the mutual information of any mapping, plus or minus an expected cost, where cost is defined the usual way in terms of constraints or prior preferences. So one can actually look at this fast structure learning as a particular kind of active inference, but not about, it's not active inference over states or active learning over parameters. It's active selection of the right model in terms of the size of the likelihood tensors and the transition tensors, and the criteria for whether we accept a new latent state or a new transition is simply, does it optimize or improve the expected free energy? Namely, does it preserve or conserve or maximize the mutual information? So we can actually look at this structure learning as just another instance of active inference, but here deployed in terms of Bayesian model selection, or some people call this structure learning, that has exactly the same rules as planning and accepting parameter updates, provided they maximize expected free energy as well. The application of this kind of fast structure learning to these renormalizing models looks complicated. Here's the algorithmic description of it. Again, please don't worry about the details here. It's relatively simple. All we're doing basically is ingesting observations, but we're just doing it for local groups. And then we are combining the initial conditions and the paths into new outcomes for the next level. And so because we are doing this for local groups, the number of groups just gets smaller and smaller and smaller as you get higher and higher and higher. But obviously the number of combinations of paths and initial states increases as you get deeper and deeper into the model. And you may be asking, well, how do you bound that? How can you possibly assimilate all the data without having an extremely large number of latent states very deep in the model that are now encoding, effectively evolving patterns or paths over quite a large number of time points into the future? Well, it's trivial to do that because the size of the highest level, I'll call them generalized states that basically generate paths and initial conditions for the lower levels, is upper bounded by the number of elements in your training set, so that you can control and upper bound the size of these renormalizing operators or likelihood mappings and transition tensors simply by giving it canonical training data, the kind of data that you want this agent to generate or this agent to recognize and thereby predict. So here's a particular example of that. What we've done here is just ask, can we very, very quickly learn a generative model that will generate a simple movie? And this movie is simple because it begins and ends in the same state, so it just loops over and over and over again. So we only have to supply one loop to this fast structure learning so that the model builds itself and can then be used in generative mode to generate the movie time and time and time again. So here's one depiction of the results of the learning, the fast structure learning, and subsequent inference when exposed to this kind of image. So the coarse graining here at the very bottom, in fact, uses a slightly finessed version of the spin block operator by harvesting local eigen modes or eigen images of little patches of the video to get it into a reduced or coarse-grained representation that then is just passed up using these spin block operators. And in this instance, we just need 2 levels to the model to have the highest level see the entire image. And then if we present the image after discretization using the singular value decomposition or the sequences of images to a model, it learns the model, and then we can generate little movies simply by moving through these paths or episodes. I use the word episode because, remember, these generalized states at the highest level encode paths or trajectories into over 2 to the n-1 time steps in the future, when n is the depth of the model. And these episodes themselves have dynamics, so we just go through a little loop here, go back to the beginning, and thereby generate this image at the bottom. What else can we do with these kinds of models? Well, one thing we can do is present not the entire data, but just a little prompt. So in this example, what we've done is actually show it just the upper right quadrant of the movie, and see what this this generative model believes is going on in terms of the predictive posterior in output space, in image space in this instance. Now, because during training it's only learned to recognize a dove flapping her wings, That's all it can believe is the cause of its sensations, even if those sensations are very partial. So basically what we have here is a kind of pattern completion that inherits from the fact that this generative model only knows about latent causes that constitute an entire dove flapping her wings. So even though this is what the dove is actually exposed to, it's sensing, this is the predicted, after a couple of frames, it very quickly is able to predict what it should be seeing, or what it would have seen had it been given the entire data. And another way of thinking about this remarkable ability to sort of fill in the gaps is from the point of view of compression. So just a little digression here. A lot of the Bayesian mechanics and variational inference that ensues from variational mechanics can also be likened to the same fundaments that underwrite efficient information transfer. So we've talked about maximizing mutual information in the context of algorithmic complexity and the associated universal computation. Then what the objective function looks like is basically how much can I compress this content to represent it in the most efficient way. So you can look at this past structure learning under these renormalizing or scale-free generative models as the most efficient way of compressing whatever your data you've been exposed to. And because we've compressed it in such a way that it can only now recognize a dove flapping her wings, then it can, if you like, fill in the gaps in a very efficient way when just given partial or noisy data. And I use the word noisy here because you can regard the missing 3 quadrants here as extremely imprecise data that has extremely low signal to noise, for example. So here's another example. In the previous example, we took effectively a movie or a dynamic or a system that had a periodic orbit, which was each flap of the wings. Will this work for aperiodic orbits and generally for stochastic chaos? Yes, it works. It works relatively efficiently. So this example, we used training data that was generated through creating images of a white ball that moved with a chaotic trajectory governed by a Lorentz system. So this is the kind of system that governs or is used to describe chaotic events in meteorological systems or in fluid convection. So by applying exactly the same procedures as in the previous example, we now generate, in this instance, a 3-level hierarchical or renormalizing model that now accommodates the stochasticness or randomness induced by not only random fluctuations on the dynamics of this stochastic random dynamical system, but also if there were any deterministic aspects, the deterministic chaos that ensues from exponential divergence of trajectories that now has been summarized stochastically in terms of probabilistic transition matrices here, which means that we can, having compressed the training data, we can now withhold not a quadrant, but just simply withhold the data, to stop the data, but the model will keep on generating what it predicts would have happened given the statistics of the dynamics that have been installed in this renormalizing generative model. And what we've done here is for the first few hundred time bins at the lowest level, we've basically rendered the images or the input very, very imprecise. so that everything is governed now, or everything is generated from these top-down priors or posterior predictive posteriors that inherit from precise priors because there's no precise likelihood. And then we've actually removed the imprecise input completely and just allowed the agent to generate its own beliefs about what's going on. So here, this is fairly precise in the first instance, and then we remove completely the stimulus, but it still imagines or generates its or predicts what's going on in terms of this chaotic dynamics. And then with a degree of uncertainty then continues to then generate the dynamics associated with this kind of stochastic chaos. Here's a prettier example using exactly the same technology and approach, but here explicitly talking about video compression. So we literally just presented a video of naturalistic dynamics, in this instance a little bird, a robin, feeding itself, and compressed that using this renormalizing generative model, such that we can again simply remove stimuli at certain points in the video, and yet in the agent's mind nothing has really happened, because all it knows is that if it was like this previously, then this must have happened, and so on through this, in this instance, orbit that doesn't have a closure. It's just a trajectory through from the beginning to the end of the sequence. And here's the posterior prediction after just being exposed to a couple of frames right at the beginning, in the first 6 time frames of about 120, of 80. This example applies exactly the same approach as previously, but now we're not talking about ingesting or learning or compressing images. We're talking now about compressing or ingesting sound files. And that is, if you like, a simple or limiting case of this two-dimensional compression that we talked about before. So in this instance now, what we're doing is compressing one-dimensional frequency summaries of a particular wave file or file that describes fluctuations in the intensity of a sound, that then is summarized in terms of a continuous wavelet transform, and then the succession of different trajectories in this time frequency space is then ingested or assimilated or learned by the generative model. Now, unfortunately, you can't hear this, so I'm not going to bother playing it, but this is what the agent was trained on. It's basically jazz piano. And these are the ensuing predictions in the absence of any inputs. It's being used to generate music using the stochastic transitions through various bars of music that it has learned, returning to one or other bars of the music when it reaches the end of the orbit, to generate something that sounds at least jazzy, if not. Oh no, I started it, but you can't hear that, so I'm not going to pursue that. So to summarize what we've done so far, we've gone beyond generative AI in the sense of having a true generative model that entails active inference and agency. And in the setting of these, what we are going to do now is go beyond just simply generating content, having been trained on the basis of some training data. And we're going to now consider agency by putting action into the mix. And in the setting of the simplified setting of optimal state action policies, where we can effectively ignore the imperative to maximize expected information gain or explore in the sense of responding to epistemic affordances, we can do one of two things. We can either use some universal function approximator, say deep learning, to optimize the mapping from sensory to active states to maximize the expected cost or the expected utility part of the expected free energy, or we can use active inference to realize predictions under a normalizing generative model of rewarded events. So what I'm doing here is deliberately setting up a dichotomy that tries to distinguish the active inference approach to purposeful behavior, where the purpose is provided purely by the prior preferences or the constraints, usually encoded in the C tensor, against a sort of reinforcement learning approach. And this is a rather busy slide, but I think it's probably worth just briefly rehearsing the distinctions between active inference and reinforcement learning. So the story with respect to action as a gradient flow on free energy, which basically reduces to picking those actions that maximize the predictive accuracy, in the sense that if you look at the expression for the variational free energy, the only thing that you can change is the accuracy, in the sense that free energy can be written as accuracy minus complexity minus accuracy, and the complexity does not depend upon action, whereas the accuracy does. So that picture basically says I can describe behavior in terms of a generative model that is optimized through perception in the usual way, cast in terms of, say, variational inference, that basically generates predictions about what should happen next. And then I can pick my actions to fulfill those predictions. In continuous state formulations, this would be sort of minimizing the prediction error, usually in the proprioceptive domain, but you can generalize this to any consequence of action. I'm just going to pick that action that brings about, or is most likely to bring about, what I predict will happen next. And what I predict will happen next is optimized through perception, through variational inference, based upon my learned and selected generative model. So this is very similar to sort of model predictive control, and in neurobiology could be cast in terms of perceptual control theory, which puts action in the game basically of realizing, evidencing predicted states. So I've tried to summarize that here just in terms of our Markov blanket, where we're optimizing our beliefs about the world, noting that planning in this instance, so planning as inference, is all about the paths. It does not have to be about action. It's just about how does this world unfold, and from the point of view of these scale-free generative models, we're really thinking about how do episodes follow each other, which episode is going to follow this this episode, and we can say, well, you are in control of that. Imagine a benevolent world in which everything happens according to your beliefs about how to be an expert in this particular world, and the agent can plan a series of episodes generating predictions all the way down to the bottom, which then slavishly action can fulfill just by fulfilling those predictions. So one could, in some sense, think of this in terms of controller's inference at the bottom level in the spirit of model predictive control, and planning as inference at the top level, so belt and braces, in terms of realizing active inference. In this particular example, where I repeat, we are really just worried about state action policies. Why are we worried about state action policies? Well, these are the kind of policies that reward learning schemes are aimed at, and have a similar architecture, but to my mind, a slightly more over-engineered architecture. First of all, you actually need explicit inputs, which are rewards. There are some proxy for the constraints under which the basic mechanics would normally operate. But more importantly, you're basically sending your inference scheme is basically about selecting the right policy. I've used Q-learning here to maximize the discounted reward. So similarities and differences, but we're going to focus on active inference in the particular setting of these renormalizing models, where, I repeat, planning and thinking or imagining a future can proceed at the very highest level. That has no notion of action. They're just patterns that unfold. They may or not be caused by me. I don't know. I don't care. But the action at the lowest level, the reflexes, as it were, are in a position to make my predicted posteriors come true simply by picking those actions that realize the predicted outcomes. So how are we going to leverage that kind of merely reflexive active inference in the context of building or learning from scratch renormalizing or scale-free generative models that would be apt for doing something, implementing a state action policy? And I'm going to appeal here again to this notion of active selection as one way of looking at action, which can always be at least mathematically expressed in terms of doing something if it minimizes expected free energy. And in this instance, what we can do is actually apply it not to the selection of the model, but the selection of the training data. So if we just apply the diktat that you only select something if it minimizes expected free energy, that includes the expected cost, what that basically means is I'm only going to select those data features or those training sequences that don't come along with a high cost, namely those that are rewarded. And that's what we're going to do here. We're basically going to learn to play a very simplified game of Pong, where this ball bounces around inside a circle. And we can move the bat in a way to return the ball so that we can avoid penalties when the ball hits the upper boundary and secure a reward whenever there's contact of the ball and the bat. And how can we learn this kind of dynamic, these episodes, in exactly the same way we learned the video of the robin or the dove flapping her wings? Well, what we can do is we can just select instances of random play that conform with our diktat that we cannot include those costly events. And so what we've done here is just generate training data, training sequences using random play, but omitted anything that does not, that contains a costly outcome. And furthermore, just to make things more efficient, we've restarted the random play after a reward is secured, and then just use the subsequent play if it actually attained a subsequent reward. So basically chaining together, bootstrapping together, or splicing together sequences of rewarded play, and then use that or submitting that for fast structure learning, and now we have a generative model of expert play, effectively, or a generative model that entails a state action policy that can be realized through reflexive active inference. So active data selection, and I'm sort of cartooning that here in terms of applying a certain kind of Maxwell's daemon that only lets through non-costly episodes. Basically, yes, admit this sequence for fast structure learning if there is a reward. If not, ignore this sequence. And this effectively learns or furnishes a generative model of events that lead to a reward and nothing else. So now this agent can only recognize expert play, and therefore all of its predictions have to be the predictions of an expert player. And because action is fulfilling the predictions, it will look as if it is an expert player. And here are the learned trajectories at the highest level of different episodes that we'll see shown in an alternative format in the next slide. So here's the initial starting episodes, little events here. The red dots correspond to reward. So, first hit, second hit, and then it falls into a nice little orbit, and this completes this orbit indefinitely by it's the way that it has learned. So remember, it's only been trained on random data, so this particular style of play is unique to this agent, but it is sufficient now to play with 100% performance, simply because it's now going round and round its orbit, very much like the wing flapping her wings. These are just different ways of portraying the same dynamics and the things that have been learned. The first 8 frames and then subsequent frames of expert play. This is the usual format showing the posteriors at different levels, the posteriors over the states and the posteriors or predicted posteriors over the paths, and then rewarded play as a function of the free energy at different levels, here illustrated by the red dots every time there's a hit, up until 512 time frames here. And here's this rather long orbit through 50 episodes, each 4 time steps in length, that subtends this kind of play. This is an interesting one and speaks to the fact that we've actually switched on inductive inference at the highest level. So what does that mean? Well, what we've done is just basically take each of these highest level states, worked out the sequence that it encodes just by computing or projecting down through the model. And if that sequence includes a hit, we said that's an intended state. That's the kind of state that I want to work towards through the successive 4 time step epochs. And if I want to be at some point in the future in one of these intended states, in this instance rewarded states or episodes, what states must I avoid in order to preserve or conserve the possibility of getting in or getting to one of these intended states? Basically, that's the technology behind inductive inference, and it's sort of summarized here in terms of the latent states of 50 or so of these latent states, in terms of how many time steps what's the shortest number of time steps until the intended state. And basically, as we move from state to state to state, we want to keep in the white areas here, avoiding these dead ends, if you like, from which there is no possibility of reaching an intended state. And it's really trivial to evaluate these areas that you have to avoid, because you know the probability transition matrices. So you just multiply it by itself and give a number of times, and you can work out, can I get from this state to this state? And if you can't, then you get this black area here, and you know you have to move from here to here to here to here to get to your intended state. So that's inductive inference in brief, and we've applied it at the top level. So we just told the agent, this world is under your control. Imagine imagine what you want, noting that these particular episodes or events contain, are things that you should pass through or should experience, and then deploying inductive inference to basically predict what will happen all the way down at the bottom, and then using reflexes to make that happen. We can apply exactly the same technology or the same procedure to different kinds of games in a slightly more complicated game. It's meant to emulate Breakout, where we've introduced certain stochasticity in terms of the initial conditions and sticky action, but the overall behavior is the same. It's just basically choosing paths through episodes into the future, given what it knows that can be achieved in order to get to rewarded states. So effectively, what we've done is create an attracting set of episodes at the highest level of these scale-free generative models, where all the allowable paths and paths that now in this generalized state space or event space lead to reward. We can go a little bit further and just add in various episodes by merging or assimilating new data, new training data, if and only if the path actually leads to an existing part of this attracting set, and I've just illustrated that here in this final example. So this is the path or the orbit or the attracting set that was learned at the highest level by the ping pong playing agent. But now we can fill in this effectively allowable dynamics to include all states that lead to a path on the orbit, or thereby all paths will eventually lead to reward or to roam. So we can augment the model of expert play with paths that lead to an orbit, namely this attracting set, and paths that lead to event that lead to the orbit recursively, and get quite a dense set of allowable transitions that we can be guaranteed always keep within the attracting set that will contain these preferred states or states that we have constraints where we have constrained those states that are not visited simply because they cannot be recognized. And that's it. Thank you very much indeed.
Amazing, Carl. Thank you. Awesome. Okay. Arun, if you'd like to lead in with a first question, and Lance too. Thank you, but go for it, Arun, first.
Yeah, thanks very much, Carl. So my first question is based on a sentence in the paper, which talks about any model being sparse must be renormalizable. Could you say a little bit more about why that must be?
Oh, I can't remember. Give me a clue.
I'm presuming it has to do with Markov blankets. And
yes.
Yeah, that's as far as I got.
I see. Yes, no, I remember now. It may have been in reference to some work done by Dalton, showing that with probability 1, provided the system is large enough, there will be Markov blankets, and as soon as there are Markov blankets, there is now an opportunity to take Markov blankets and Markov blankets in the spirit of that applying the renormalization group that I started off with. So as soon as you've got, as soon as any sparsely coupled random dynamical system can now support a particular partition into Markov blankets, you've now got the opportunity to take Markov brackets and Markov blankets and then apply that renormalizing procedure that I said before. So all you need to posit is any system that has a Markov blanket at any given level. And as soon as you've got that, you've got Markov blankets all the way up, not necessarily all the way down, but you've certainly got them all the way up. The physics approach would actually also require for there to be Markov blankets all the way down as well, but that's another issue. What that basically means is that all you require is a sufficient degree of sparsity that would lead to the conditional independencies that are definitive of Markov blankets. And in one sense, much of the sort of the maths behind the free energy principle as it inherits from random dynamical systems, or in physics, say, Langevin equations, is simply showing that a sparse coupling, a sparse causal coupling in a physics or control theoretic sense, not a philosophical or Granger or cause-effect structure sense, but in the physics sense of a coupling, so that the change, this state influences the rate of change of that state. So that kind of, which could be written as an influence graph. So if there's a sparse coupling on the influence graph, the equivalent Bayesian graph or probabilistic graphical model induced by that sparse coupling now can be interpreted in the sense of Pearl's Markov blankets. So all you need to get to the application of the renormalization group to Markov blankets is sparse causal coupling, hence sparse random dynamical system that is sparsely coupled. Just out of interest, the spin block, the motivation for the spin block, applying the spin block or blocking transformations, that basically comes from the assumption that many systems that people deal with, both in computer vision and in idealized models in physics, has an exquisitely sparse distribution, and that's because the causal inferences are all local. So as soon as you look at a coupled map lattice or a globally coupled map, you'll notice, let's take the lattice for example, let's take a sort of idealized crystal. So what you're saying when you write down a lattice is I'm only connected to my neighbors, to my Moore neighborhood, or to my Markov blanket. That means that in a large lattice, where I could be connected to n squared neighbors, I'm only connected to 1, 2, 3, 4, 5, 6, 7, 8. So a fantastically small, almost empty set of possible connections. And I use that phrase because there's, I can't remember who said it now, but I really liked it. The notion that if one looks at the connectome in the brain, in terms of the connections, it's almost empty. The number of actual connections, white matter connections, external connections, and indeed intrinsic external connections, are almost zero in comparison to the total number of possible connections between the 10 to the 11 or whatever neurons in the brain. So that's not surprising, and it's one of those nice examples that the anatomy, the functional architecture of the brain recapitulates the anatomy of the lived world. In that it has this incredible sparsity, and that just means that universes in which there is the action at a distance is quite rare. Means that you're just interacting, you're just coupled to your neighbors, and that gives you, if you then look at the Markov blanket structure or the particular partition for these lattice structures, you get to the spin block, the blocking transformations, as a way of carving up nature, in terms of little patches on Markov blankets.
I do have a follow-up question on that, but then I'll hand it back to Daniel or Lance. So the lattice example is really interesting because I think there's a symmetry there that maybe we lose when we talk about blankets that only have one parent. So in a normal lattice, as you say, you're just connected to your 8 neighbors in 3D space. When we looked at the spin block transformations before, we were going, let's look at this square, and everything in this square has one parent, but then the square along is connected to a separate parent. So now if you're at the boundary, we are breaking some symmetry there.
Yes, technically or practically, a very good point. It doesn't really, it doesn't really have any material impact upon the algorithms or the partitioning. So just practically what happens is you just take your tiles and then you have a half tile or a partial tile until you get to the boundary. So these groups in the grouping operation or the blocking operation are not necessarily the same. They're not the same size, and indeed in current work, we're actually dealing with sort of multiple streams. So you can have sort of audio files and video files separately tiled and then converging right at the top. Ideally, what you'd want to do is not use this blocking transformation, but to try and identify the Markov blanket structure at the particular scale in question and actually use the Markov blankets based upon well, there are a number of ways of doing that. You can either use a Markov blanket discovery algorithm of the kind that Jeff Beck works upon, or you can use empirical analyses of the dynamical coupling by estimating effectively the Jacobians. For those people who are interested, there's a worked example of that in the Particles and Parcels in the Brain paper in Network Neuroscience. It's really framed in terms of data analysis, but you can use the same principles to identify a particular partition from a large number of states or voxels or pixels in 3 and 2D respectively. There's another thing though that I think your question speaks to, which is you've got one block of 4 and then another block of 4, and then because of the sparsity, they're separately modeled at the level above. So I thought you were going to ask, how on earth now do you start to repair the obviously rather facile assumption that you've got just local action? Because of course in our world there's lots of action to distance. We are talking to each other over thousands of miles or kilometers, and we have vision. So all and we have linguistic communication via sound. So it is interesting that we have actually violated much of the local action. If I was a virus, this would be perfectly okay, because the only thing that's really going to affect me as a virus is the things that actually are in molecular contact with me. But for you and me, and the worlds in which we live in, we can't. There is no such thing as just the action to distance now starts to really matter, and effectively because the two latent states, generalized latent states, generating stuff, initial conditions and paths for the 2 blocks below, because they themselves now constitute contribute to a single latent state at the level above. As you move deeper and deeper, you start to now repair the simplifying assumption of conditional independence between the groups. So it is at the higher levels that you're able to see this action at a distance, these coupling. What happens over here really matters in terms of what's going on over here, but you'll only ever see that. You only have that as part of the generative model right at the top, which is why all the inductive inference is implemented right at the top level where you can see everything. So that it becomes, if you like, you are now in a position to model and thereby generate appropriate predictions that rest upon these long-range dependencies. And of course, using the word long range, I mean in the sense of the coupling distance, from, in a dynamical sense. Is that what you had in mind?
That was exactly what I had in mind. Thank you.
Thank you, Arun. Lance, do you have any remarks or want to add a question? Or I can, yes, please go for it.
Yeah, I have lots of questions. Thanks a lot, Carl, for the talk. So I'm just wondering about this all roads lead to Rome slide that you had at the end. And I'm wondering whether you have some sort of a curse of dimensionality as you increase the dimensionality of the system. So it sounds to me like the manifold of expert play, because you're taking temporal trajectories, that's going to be a one-dimensional manifold. Now, as the state space of the game increases in dimensionality, you're going to have an ambient space of trajectories that's much, much higher dimensional. And so it sounds like the amount of trajectories they need to, construe to bring you back to your one-dimensional expert manifold is just going to grow and grow and grow. And it sounds like it might be hard to fill that space. So could you comment a little bit on that and whether it's a problem?
Right. Yeah. In general, in my world, these things aren't problems, but they're challenges, and I think that challenge is yet to be met. So what I imagine people will do is that you will ingest extra episodes or sequences that bring you onto your attracting set up until some bound, and then you will switch off active selection, by which I mean the structure learning. So you stop growing the model, and then you switch on parameter learning, so that now you're forcing the transitions and the expression of various generalized states to accommodate variations around the training data that you have been previously exposed to. So that fixes the size of the tensors and hence the dimensionality of the state spaces in question, but will, in principle, now accommodate by using sort of active learning, in the technical sense that you only update a parameter if it does not increase expected free energy or decrease mutual information. Then you're now in a position to become more robust. And perhaps I should qualify this answer. The whole point of this adding in extra, if you like, insets onto an attracting set is just to equip the agent with a certain robustness should itself find itself outside or off that attracting set. So I know Lance knows this, but I'll just make this explicit for everybody else. This kind of learning and state action policy implementation is very much like learning to ride a bike. So you basically just accumulate and remember those experiences that were successful. So, for example, I managed to rotate the pedals by one cycle and I don't fall off, and I remember that. And then I have another go and I wait until I've actually done 2 cycles and I don't fall off, and I remember that. I forget everything every time I fall off, and then I keep on going until at some point I connect back my last cycle was identical to the first cycle, and then I've learned to ride the bike. But because I've forgotten all the falling off, I can't recognize or know where I am when I've fallen off. So I've got a very brittle expertise that will not allow me to recover if I fall off the edge. So another example which makes this slightly clear, I think, is like mountain climbing. If I want to be an expert mountain climber, I cannot learn by my mistakes, provided I'm climbing a sufficiently high mountain. Should I fall off it, then I will die. Another example here is learning how to cross the road as a child. You cannot learn by experiencing being run over. But the cost you pay, or the price that you pay, is you can't recognize when you are being run over. And that, I repeat, lends a certain brittleness and a lack of robustness to agents who may be exposed to danger that doesn't actually terminate them. So putting this robustness back in by growing the attracting set, or basically putting these insets on in this sort of generalized phase space, it's just to make it more robust. In numerical studies, it does seem to converge. It doesn't seem to grow indefinitely. So those are likely violations are moving off the attracting set are themselves quite small, relatively small in number. Practically speaking, if you've controlled the sources of stochasticity or unpredictability. So it may not be always the case that you need to have an explicit bound on the size of the very high level tensors. If you do, then one has to now think of a principled way of making that upper bound an emergent property of expected free energy minimization. It may be that you violate now the mutual information, that certain rare events are just so rare you're actually compromising the mutual information by including them as a particular option or a particular column of a likelihood mapping. But I don't know. But these are all really interesting questions to pursue.
Thank you, Carl. All right, Arun, go for it.
So following on from that, I think there's an interesting question on the uniqueness part of ingesting data. And the question is, are there many more ways to fail than there are to succeed? So if you're passing your data into our sort of Maxwell's daemon with a gate saying, accept this data, reject this data, if this improves my mutual information. If there are many more ways to fail, but then get back onto the successful path, but there are only a few paths that actually keep you there, would it not make sense to just continually accumulate these sort of recovery states? Because the mutual information will keep increasing, and then you stop there. Then you learn parameter-wise, because we're not including the sort of prior distribution of how likely you are to be succeeding at any given moment. Because with the uniqueness thing, you don't know, 10 times out of 10, I'm cycling. Or like 9 times out of 10, I'm cycling, and 1 times out of 10, I've fallen off the bike.
Yeah, I think it depends. Again, I don't have any explicit numerical analyses or mathematical analyses of this, but intuitively, I think during learning, there may well be good mileage in ingesting failures or routes to success, if you like, or to the attracting set that actually traverse regimes that would normally be excluded by my constraints or my prior preferences. Just taking the view of the role of the C tensors or prior preferences from the point of view of physics, what that basically is saying is it's actually carving out vast regimes of state space, latent state space, that you should not be in, because it would be uncharacteristic of you to be in these things. So it's really not so much about the rewards and the preferences. It's really where you shouldn't be, and that's what defines the attracting set. However, before you've learned that attracting set, it may be useful to include constrained regions of state space that offer a route into or onto that attracting set. So I can certainly see that would be a useful device. But notice that once you're on the attracting set, you will never visit the constrained regions, because you now keep yourself on the attracting set. And therefore, if you've encoded those, but you never visit them, your mutual information will actually fall. So what that means operationally is what you probably do is have this sort of slightly over-inclusive structural learning. learn how to cope with all the necessary sources of randomness so that your attracting set is sufficiently robust, and you do actually visit from time to time, but not never. Sort of excursions from the attracting set are drawn back onto the attracting set, and then use Bayesian model reduction to eliminate all the states that you don't want to recognize simply because you never go there. Once in a, when I was younger, I would certainly be able to recognize what it's like to fall off my bike. But now, as an expert bike rider, I really don't want or need that. So, and that's just basically getting old and wise, and implementing Bayesian model reduction to remove the redundant parameters, which would, in this instance, just be the columns and associated slices or rows of the transition matrices. So I think you could, perhaps another way then of answering Lance's question is, you just keep accumulating, but start to engage Bayesian model reduction. At some point you should reach an equilibrium, which will be the attracting set that allows you to survive in the characteristic states that define you in this particular environment with this particular volatility.
Thank you. Awesome. Okay, I'm going to bring in a question from the live chat. Okay, Javier wrote, so stochastic plus dynamical probabilities learned by the agent itself are scale-free. Will this hierarchical learning also be applied to the goals of the agent, different abstractions, granularities of goals self-learned?
My answer would be yes, but I'm going to ask Lance to answer that one.
Oh, that's cheeky. Yeah, I would say for sure. Because typically when we operationalize the goals in our generative model, they need to have the same structure as our generative model itself. So I would imagine then we would have hierarchical renormalizable goals, which kind of makes sense.
Cool. Okay, I'll bring in. Oh yeah, go for it, Carl.
But I was just going to say, just to unpack what Lance just said in terms of practical things, if you're trying to say, what my goal is to have dinner. That naturally unpacks hierarchically into, I've got to move from the living room to the kitchen, then I have to find open the fridge, and I have to find the food, which then unpacks into, I have now opened them, and all the way down to the finest muscle movement. So almost by definition, intended narratives can always be decomposed in this scale-free way, this is very similar to sort of motor chunking and hierarchical decomposition in theoretical motor control, for example, and you probably find it a lot in robotics, that there's a sort of global long-term plan that provides empirical priors or constraints on shorter little chunks that themselves provide constraints on shorter and shorter chunks, and that's exactly the if you like, the architecture implicit in these scale-free models.
Awesome, and totally ties back to the synergetics. Okay, I'll ask 2 questions from ML Don. He wrote, how can we inject the same separation of timescales by imposing smoothness constraints on, say, the parameters as opposed to playing with proportional update rates at different levels? And this relates to something Arun and I talked a lot about in the .0 and leading up to it, is identifying which windows to use. You could imagine picking the right separation of timescales. If the classes on campus really do shift on the hour, then the hour course grading is going to be great and effective. But the 59 or the 61 minute might alias you with the real variability of the system, and so there's not necessarily even a smooth landscape for determining the windowing or the binning of coarse graining. And coarse grainings may have dependencies on each other. So how do you go about playing and finding viable approaches and robust ones amidst all these different levels of meta optimization that are opening up?
Right, I'll take this one, and Lance could take the next one. Then that's a really good question, because there is an implicit separation in timescales between so vanilla implementations of inference and learning. However, in these schemes, there isn't. So the MATLAB version or implementation of active inference under these, and in fact all Markov decision process models, unlike the procedures that you might find in data analysis, where you acquire, you basically do some filtering on an epoch of data, and then at the end you update your parameters, and then you rinse, wash, and repeat. In active inference simulations, and also in some applications of what's called generalized filtering, you have continual learning. So the update of the parameters actually occurs at every time step, at each level of the model. So the likelihood parameters at the lowest level are updated every time that routine is called. So there is continual learning. The learning is, yes, you're absolutely right, it's smooth in the sense that you're slowly accumulating Dirichlet parameters, but the temporal scale of that learning is the same as the inference. And you could also argue, well, could one also put Bayesian model reduction into play at the same timescale? So basically, can you at every time point, at each level in the model, identify redundant parameters and remove them using Bayesian model reduction? In effect, that's what's done using active learning. What I said before, active learning will only proceed if the expected free energy on mutual information improves. That's actually also implemented. So the rate at which it looks as though things change between inference, learning, and model selection is certainly distinct. I don't think that's quite the same kind of separation of timescales that is implied in the renormalization group. That's, as you were intimating, Daniel, exactly specified by the number of ticks or updates at level n per single update at the level n+1, and that is, I think, the key question you're asking. How do you get that right? And of course, the answer to that is the model that has the greatest model evidence, or smallest free energy, or greatest marginal likelihood for the kind of data generated by this environment in this world. So are there any sort of useful priors you can put over this? Well, one useful prior is that things are changing as well, one prior which is actually used in operation is you take the lower limit on what's called the temporal RG flow, which is basically the length of the window at each and every level. At the moment, that's 2. What does that mean? How can you motivate that? Well, it's the most expressive in the following sense. But if I just imagine what this discretization of time means from the point of view of classical notions in continuous state space, like position and momentum, or position and velocity. If I use a scaling of 2, which is basically means there are 2 time steps for every time step of the level above. What I'm effectively doing is modeling 2 time steps for every state at the level above, and that basically means I can model the initial condition and the subsequent condition, basically in terms of the change, which of course is the velocity. And what does that mean for the level above that? Well, it now means that I'm modeling the change in the velocity. So I'm now modeling the acceleration, and then so on up until the highest order of motion. So what that means is by taking this limiting case of T, the temporal horizon, or the ratio of time steps from one level to the other level, as 2, means that I got a very expressive model that can handle, can recognize things that change very, very quickly in their acceleration, their jerk, and the implicit context sensitivity that gives you. If I didn't do that, I'd have to assume that I coarse grain over long periods of time, and therefore the path is consistent during that time. Now, that sometimes is a useful approximation, and indeed there's a whole industry called switching linear dynamical systems that makes that approximation. And it means you can approximate all the nonlinear, complicated, high-order motions in some evolving pattern or system with a series of linear trajectories that basically go, that intercede between a series of points at which you switch. The problem with that is that the length of the linear trajectories, for us, for example, I'm committed to one path U, so one slice of my B matrix for the next 8 time steps. The problem with this is that you don't know when you deviate from that transition dynamics. So then you get into the game, well, perhaps I could make my scheme reactive. So sometimes I do 3 steps, sometimes I do 8 steps, sometimes I do 1 step, and I have some criteria for saying your predictions about my trajectory have now been met. Please, I'm going to give you the evidence that I'll be pursuing this path. You update your primary level above and tell me what you expect me to do next. So this now speaks to a particular kind of reactive message passing that starts to have implications for the computer science and the sort of the CRD, the CRUD, as I think we've rehearsed before. At the Institute, the original conception behind the actor model in computer science from the 1990s. So it's all about reactive message passing. I will send you a message when you send me. I will return a message to you if you send me a message. And what these renormalizing time models have, and I should say that this also applies in the absence of the spatial renormalization, so any deep temporal model will have this aspect. What that means is that from the point of view of any given level, I will be responding to messages more quickly from my subordinates than from my superiors. So once in a while, I'll get a request from a superior. My response to that is to ask my juniors to do a series of things. They report back to me, and when they report, I give them the next bit of request or guidance until they complete their job. And when all my juniors have completed their job, and of course in the renormalizing, spatial renormalizing context, I'll have a whole group of juniors to worry about. Then I have gathered enough evidence for me to then return the message to my superior. So you get in terms of the reactive message passing in this sort of actor model of computer message passing, you get the separation of temporal scales inherits from the number of messages or requests and responses exchanged with the people lower down in the hierarchy relative to the number immediately subordinate. And in principle, they don't have to be fixed. So there could be a criteria before I pass the message back up to the higher level. I think that's, Daniel, probably what you were getting at. I'm not. There may be somebody who's done that, but I haven't done that, and I don't know. I can't give you an example of somebody who has done that. You may find somebody in Bert de Vries's group, who are sort of some of the world experts in reactive message passing who have considered these kinds of things. You know, in principle, there should be a way of each level testing whether I have fulfilled the predictions of my superiors, and now it's time to get more guidance, based upon the free energy.
Awesome. The organizational technology I didn't know that my PhD needed. Okay, I'll ask a question as we get close to the end, and this will be for anyone. ML Dawn wrote, how does the training time of active inference compare to that of reinforcement learning, and how does their scalability compare? And it would be interesting just to hear anyone's very 2024 takes. Where are we at with that entire arc from problem conceptualization on through the training and the inference? How do we even grapple and describe with similarities and differences in the training time and resources and all of this?
That's definitely Lance for at least 5 minutes, I think.
I'm a bit incapacitated in terms of talking. I think this is actually a good question for Arun. But yeah, I mean, I can say a few things. So scalability in active inference, I would say it has been a challenge, and there has been much less man work hours that have been put into that than in reinforcement learning. Now, for the past few years, we've had a lot of work, a lot of it led by Carl, actually, trying to scale the structured learning in active inference. And I think we've done a lot of mileage on that. So there's been the supervised structured learning paper, there's this paper. There was also some interesting work presented at the International Workshop on Active Inference. I personally think there are still some challenges ahead, and I think one of them is the one that we just talked a few questions ago about. If you learn an expert orbit, how do you get back on the orbit as the dimensionality of the system increases? So this is definitely one challenge. Now I know much less about reinforcement learning, so yeah, maybe Arun has more things to say there. But what I will say is a lot of reinforcement learning is powered by deep neural networks. When we use deep neural networks, we sacrifice the interpretability of our generative model. So this is one of the strengths of active inference, is having more interpretable dynamic causal models where we can actually peer into them and see, okay, well, this representation encodes this other one encodes that, and so forth. The fact, though, that reinforcement learning typically uses deep neural networks means that it has been much more scalable, just because there has been so much work done in training deep neural networks. So this is a bit of my my perspective. I don't think it fully answers the question, though.
I can come in with a little bit on that, but I must admit that I have not trained any reinforcement learning agents myself. I have worked with people who have. I'd agree, Lance, that the infrastructure generally is much more advanced for training RL agents for doing stuff, and completely agree with, as you say, the explainability and the interpretability of why did an RL agent pick a particular action is very opaque. And I think the deeper those networks become, the harder it is to understand what's going on in the hidden layers and generally why they do what they do. I think with active inference, yes, we do have more explainability, but I do wonder if we go the fast structure learning approach, think Carl had a particular comment earlier about looking at the highest level, identifying the desirable states learned by the agent. From what I understand, the identification has to be done by a human. They have to look at the model that's been learned by this renormalization approach, look at those top levels, and then say, what do these levels mean? So an example in the paper is the MNIST classification. It's the case of a human being looking at those top levels and going, these top levels each correspond to a digit in the handwriting task. So we are sacrificing some explainability, I think, by doing this fast structure learning compared to what might be the old-fashioned way of creating generative models by hand, by thinking, sitting in my armchair and thinking, this is how I might model the world, these structures, these likelihoods, these states. And when you do that, I think just by hand, you have 100% explainability. That model just might not perform very well. So I think there's always going to be that tension there. But in terms of how quickly these things learn, having not trained either, I'd be having a reckon. And at the moment, I would say probably an RG active inference agent would train faster, simply because it's able to use the structure in the data much more effectively. That would be my take. And I think as well, really interesting thinking about the active data selection part of this too. I know that there is some stuff in the paper about the efficiency being both a curse and a burden, but I'll hand over to Lance and Carl to give more details on that.
Yeah, Lance?
Yeah, just to echo what Arun said. Also, so the structured learning and active inference and in reinforcement learning is also very different. In reinforcement learning, we typically have a model with deep neural networks that's massively over parameterized. But it has some fixed representational capacity from the outset because the structure of that model will be specified. And then typically the model will learn, and then probably you would prune it using some techniques like dropout or other things. If we looked at that from the perspective of active inference, it would be like specifying a massively over-parameterized model and then pruning it with Bayesian model reduction. But now in active inference, we have this Bayesian model expansion, for example, in this paper. And what this Bayesian model expansion does is it learns from the get-go the minimal model for explaining the data. And so in that sense, it's extremely efficient and also provably because it extremizes the marginal likelihood or the mutual information.
Yeah, I just wanted to echo that last point. That's a really important point. So Lance is drawing the distinction, and there are many distinctions you can draw with deep RL and deep active inference, read in a more in its generic sense, and that distinction at the level of structure learning or model selection, I think, is absolutely crucial. So, deep RL starts with an overly expressive model with a known functional form that is deliberately over-parameterized and then shrinks it or reduces it to maximize the mutual information, the expected free energy, sometimes referred to as a cross entropy in machine learning. So the reward function now becomes there's no explicit reward in unsupervised learning. It's just replaced by the mutual information or the cross entropy, which should be distinguished between supervised reinforcement learning, such as digit classification, for example. Whereas the active inference under fast structure learning is exactly as Lance says. It starts from nothing and stops when it's minimally complex, which means it's maximally efficient, and that efficiency translates in many guises through to sample efficiency, through to statistical efficiency, through to thermodynamic efficiency. And this matters because from the point of view of climate change, this is the right way to do it, as opposed to building power stations to power large language models and transformers that need big data. So the efficiency on all levels, whether it's the sample efficiency or using the right data, or whether it's right through to how much electricity do you need to actually train your model, and how many millions of dollars do you need to train a foundation model, all of these are reflections of the failure of machine learning to write in the efficiency into the ultimate objective function, which, as Lance said, is just the marginal likelihood or the evidence for this model of this kind of content or world.
Awesome. Okay, final question, and a very apt one as we head into the rest of the symposium. So just give any short thoughts. Tintin wrote, "Hi all, thanks for the incredible event. Does the sequence in which the training data is fed to the AI structure learning model impact what the resulting learned structure would be?" So the learning curriculum, aka symposium program challenge.
Well, the answer is, sorry, I'm mindful that Lance is recovering from his jaw surgery. Yeah, absolutely. And this is, again, just in relation to the last question, something I think that it eludes conventional RL, certainly that it rests upon classification procedures, because the active inference as an application of the free energy principle is all about the dynamics of self-organization. And dynamics means time, and time means sequence matters. So inevitably, at some level, the order in which you see things is absolutely crucial for getting the right kind of generative model. That is even in the case, actually, of static image recognition, because you're assuming that there's no ordinal structure or correlation structure to the presentation, say, of MNIST digits. You're assuming that they are selected at random, as opposed to seeing all the tens and then all the ones and then all the sevens. So even in these edge cases, which are the focus of 20th century RL, static image classification, for example. Order does matter, but it matters absolutely acutely, because, of course, the order in which you see content in this in fast structure learning determines how you populate the transition tensors. And it's the transition tensors that enable separation of temporal scales, that enables the ability to encode narratives and plans that far transcend the actual rate at which you sample the environment. You could also argue that this issue has emerged in a strange kind of guise in transformer models. So the attention heads operate on the past. So the where you select from the past in terms of which token is going to predict the next token most efficiently, again, is exquisitely dependent upon and sensitive to the order in which you train these models. So, Daniel, have you thought carefully about your ordinal approach to this?
I let the structure of the niche and others' constraints provide the first pass and make requests from there. So, thank you, Carl. Thank you, Lance, for joining again. Thank you, Arun, for all the contributions with the .0. Carl, great to see you. So, next up, we'll take a 30-second break, and we'll be back with Michael Lennon. So, thanks, fellows. See you soon.